Hello friends, good morning, namaskar, and welcome in this new lecture after a long gap between previous lectures and this. I'm sorry for that, and I hope you all are fine and enjoying sister learning and doing good papers related to this wonderful field. So Dr. Mohan L Verma from Computational Nanoanic Research Laboratory, Department of Applied Physics, Sri Shankaracharya Technical Campus, Bhilai, Chhattisgarh, India. I welcome you all once again. So the topic of this lecture, this is one awaited lecture by research scholars and researchers that was related to the calculation of effective mass. And you are aware of that particular term, that effective mass. This is different from free mass. And this is the term related to, in general, applied for the semiconducting materials and for optoelectronic devices, semiconducting devices, where one wants to calculate the effective mass of electrons as well as holes. So in this lecture, we will deal about the calculation of this effective mass of electrons and holes by using the band diagram. So this lecture is divided into two small parts. So one is one small PPT presentation, and then obviously that lab demonstration how to calculate that effective mass. So first of all, let me share my screen. So this is the first part of that lecture, and you are familiar with these terms, that effective mass, and that this is the formula which one can easily derive this formula by using simple solid state physics books. And the fundamentals are really very simple, and it's related to the electron's energy, which is related to frequency of electron waves. And here we use the concept that electron as a wave, that the concept of matter wave, and there is a concept of group velocity, which is denoted by this Vg, and this is denoted by decay, and further one can calculate, derive this relation. And so interpretation. So these electrons are not free. This is the effect of internal forces as well as external forces. Internal forces that will be in form of ions and core electrons in that crystal lattice, and external forces that is the applied electric field. And that mass in presence of these internal and external forces, that is known as that effective mass. We will calculate that effective mass. So this is that external force, which is equivalent to Q multiplied by T, and that internal force that is in the direction opposite to this external force, and this is because of this ions and core. Now that electron acceleration, that is not equivalent to that external force upon this ME, but this is actually equal to that external plus internal force upon ME, which is further equivalent to F EX upon M star. This M star is that effective mass. And that dispersion relation, we can compensate for the internal forces due to the crystal and allows us to classical concept for the electron, as long as its mass is taken as M star, that is effective mass. So these are that familiar diagram you are using in your solid state physics. This is a band diagram, and we have discussed the details of such band diagram in one of the lecture, and how to calculate, how to plot that EK diagram, and for a crystalline structure or periodic structure, and that detail using that GNU bands type tools and that Siesta, that is the inbuilt tool. So I'm not going to the details of this, and this has actually the directional effect that along x-axis, and this is along y-axis. So accordingly, if you want to calculate that effective mass by using this band diagram, so you will get effective mass along x-axis and y-axis. So I would like to say that that effective mass has the directional effect. And some further notes about that EK, you have the concept of indirect band gap semiconductors and direct band gap semiconductors, and it's a simple familiar terms. If this band gap is measured for two different symmetric points like that, these and these, that is known as indirect band gap, and this is for the silicon cubic structure. And for the direct band gap, if one calculate that band gap for the same k points, that is k is equal to 0, then that is known as direct band gap. So these are the simple concept, and I know you all are familiar with this. Now, the determination of effective mass of electrons and holes using EK diagram. So we will use this formula. Formula is equal to m star, that is h cross square by del square E by dk square. So double differentiation of E with respect to this k, where this k is the wave vector and E is that energy. So here this h cross, that is 1.05 into 10 to minus 34 joule-second. So from the methodology is simple. From EK dispersive curve, we can get the value of this second derivative of E with respect to k by using the curve fitting of parabolic curves at any particular symmetric points. And in general, we will take that minimum energy value of conduction band for electrons and the maximum energy value of valence band for the calculation of effective mass of force. So for the curve fitting, we will take that parabolic part, and this is that general equation for the curve fit, that E is equivalent to A naught star k square plus A1. Sorry, this is multiplication by k plus A2. So here this A naught, A1, A2, these are the coefficients. And here this E, it is in electron volt, and k, that is equivalent to 2 pi by lambda. And this k will be in 1 upon angstrom. So or 1 upon nanometer. So generally in EK diagram, we take this in angstrom. And when we calculate the double differentiation of this, then we will have this 2 multiplied by A naught. So the effective mass, the formula for the effective mass will be, by replacing this term with that 2 A naught, that will be equivalent to h cross square by 2 A naught. So if you want to calculate that effective mass at any particular symmetry point, then just we have to find this coefficient of this k square term. So for the calculation, first of all, let's check the dimension of this coefficient A naught. So since we have this, E is equal to N naught multiplied by k square plus A1 multiplied by k plus A2. And here this is in electron volt, I have mentioned earlier, and this k is equivalent to 2 pi by lambda. So the dimension of this will be equivalent to, by calculating this, we will have this EV multiplied by angstrom square. So after putting the value of that angstrom and electron volt into form of joule and meter square, we will have 1.6 into 10 to the power minus 39 joule meter square. So this is the simple calculation. So m star, that is the effective mass, is equivalent to h cross square by 2 epsilon naught. So here this h cross is 1.05 into 10 to the minus 35 joule square multiplied by this. And when we convert this in the form of kilogram, then we will have 3.445 into 10 to the minus 30 upon A naught multiplied by k in a kg unit. So we have to calculate this A naught, and when we put this value of A naught, we will have definitely the value of this m star. So this is the simple method of calculation, and you may have some error during this conversion. That's why I have mentioned here. So here the coefficient obviously will be calculated from the curve fitting of EK plot. So this is the calculation which we will perform in the laboratory, that the computational lab. Here we will use this formula, and I will take one small part of that curve, parabolic curve of this k point. So this is that part of the same band diagram which I have shown in the last slide. And just I have taken that small parabolic part of this, and by using that curve fitting tool, I will get this this type of output in our XMGrace tool. And you can also use some other plotting tool to get the curve fitting equation. And then this A naught is equal to this. So by putting this value, this is that value, and after using that calculation, we will have this 2.9 into 10 to the power minus 31 kg of effective mass of that electron. And that this is that conduction band. So the lower part of this conduction band, this will give the effective mass of electron, and the upper part of this valence band, this will give that effective mass of hole. So one thing which I would like to mention here, if this curve is broader, then you will have the heavy holes, and this, if that curve is sharper, then you will get the lighter holes. So in the solid state physics book, there is the concept of lighter hole, heavy holes, and lighter electrons, heavy electrons. That is categorized on the basis of this EK diagram in terms of this wider and this sharper parabolic curves. So just I have taken this that wider part here and performed that curve fitting by using that XMGrace plot, and I obtained this value of A naught is equivalent to minus. Here this will be with minus sign. So this minus sign indicates the mass of hole. So this is just one schematic calculation. So if you take some more points, then you will get different values of A naught, and you can take the average of that, and you will have that value of reliable value of that mass of holes. So for the mass of holes, you have to take the upper part of this valence band, and for the calculation of that effective mass of electrons, you have to take the lower part of minimum value of this energy of this conduction band. So for indirect band gap, just here this is that SI cubic, so this is indirect band gap in the semiconductor. So we have taken this term, this is that lower part, that is K pi, and for the calculation of effective mass electron, and for hole we have taken this this part that is at the zeta point for the calculation of holes. So these are the things. So just again I'm repeating the same. If that curve is sharper, then you will have the light value of M star, and if this is widely opened, then you will get heavy holes or heavy electrons, because you will have a smaller value of del square by d square. Now let's make the calculation in lab. So I'm coming out from this part, and let me go to that lab part, demonstration part. So this is my folder for the demonstration of so this is effective mass terms. So I am taking the example of this SI cubic here, and this is that. So before that, this demonstration, this calculation, I performed the optimization calculation by using this optimization of cutoff, key points, latest optimization, and the final optimization. This, and then for the band diagram, as I have mentioned in my previous lectures, we need that additional this flex, this blocks, in order to get the star.bands file, and by using that the GNU bands, and if we get this from CK path or X crystal. So I have given the details of all these in one of my lecture. So if you want to the detail of this, then you can go to that. And after getting after running that FDF file, so you will get this bands, and by using GNU bands, you will have this bands.det. So first of all, I'm opening this terminal, and let me plot this bands.net. So I'm using XMGrace here, XMGrace bands.net. So this is the plot. Now let me find this plot in a specific energy value. Let me take this is from -5 to -5, and then the gape. So okay, so this is that plot for that SI cubic structure. So this is indirect type semiconductor, indirect band gap semiconductor. So I'm converting this into okay. So this is Fermi energy level is shifted to 0. So this is that Fermi energy level, and this point is K points. So one can get which one is K points or X point from this bands term. So here this is that terms at different points, G and X point. So we will start where we will calculate this U point or K point for this. So this is that K point and this is that the zeta point. So we can calculate that curve effective mass of electron using this conduction band, and this is that valence band for the calculation of force. So here what you have to do, just to click this is that term, and this point is that is about in y-axis 0.367 are along x-axis, this is 5095. So just to double click this, so you will get this data. So just keep that point, this lowest point is about 5.1. So here this is which one? This one is the 5.21. So this is that center point. So keep about 5 to 6 data along negative x-axis from this point, and 5 more points from right hand side. So you will have maximum 11 or 15 points symmetrically along x-axis and along negative and positive x-axis by keeping this particular point as the center, and that is that center point. And then delete all other points by just checking all these points using this term. So just you can delete selected rows. So these are the terms. So just to keep remaining only 10 to 12 points or 15 points by keeping this point at the center, and you will get and delete all remaining points, and then you will have one small part here, and you can also delete this remaining curve. So you can delete this by clipping this and this one, just to keep field data. So this is that the term, and you can change the color of this, which that curve which is under study. So this is that. So here you will get. So to save time, I have saved that as here, and this is for the electron. This is that point, remaining point. How many data remaining here? This is only 11. This sorry 10. Only 10 data remaining here, and other data I have deleted by using the method determinant. So now let us perform that curve fitting. So here go to this data point and the transformation, and we will now use non-linear curve fitting. So this is that non-linear curve fitting, and you can easily get that point, that is 11 points, 128 total points we have, and 11 points are here. So also in the right in this there will be the term this 11, and now we will perform that curve fitting here. So I will write the equation, that is a naught multiplied by x square plus a1 multiplied by x plus a2. So this is that equation, a naught, that curve fitting equation, a naught multiplied by x square plus a1 multiplied by x plus a2, and there we have three coefficients, a naught, a1, and a2. So let's take 3 here. So this is that the term. So here 1 1 1 is there. Now apply, accept this, you will get this. Let me expand this one. So here this is that the value of a naught, that 115199. This is that a naught, and this value we can use in that equation which I have shown in the here. This is that a naught. So when we put this a naught here, this is that. When we put the value of this a naught here and calculate this, then we will get the value of this effective mass, which is equivalent to 2.99 into 10⁻³1. Then we can compare with the mass of electrons, that is 9.1 into 10⁻³1. So we are getting that effective mass of electrons in this particular SI in this K points, lowest energy points in the conduction band, that is less than the free mass of that electron. And similarly, for the second, for the hole, we will consider this one. And I have also performed the same calculation, I think, for the holes. So this is for this was for the electrons, and this is for the hole. So I did this that I have taken that wider curve and deleted all points. So I have just how much, about 10 to 11 points remaining here. So these are that points. So I have taken that central part here, and other part of curve I have deleted. So now we will perform that curve fitting by using the same method. So using that transformation, and then it's non-linear curve fitting. And again, this is that 11 term. And again, I will write the same equation here. That is A naught multiplied by x squared plus A1 multiplied by x plus A2. So this is that equation, and I am repeating the same. So here, these are the three values, and let me accept this calculation. If everything is okay, then you will get this in that relation. So here, that value of this calculated A naught, that will be with minus sign. So this minus sign indicates the mass of hole. So this is minus 11.877, and by using that formula, you can calculate this. This is 2.90 into 10 to the minus 31 easy. So this is the simple method which everyone can perform to find out that effective mass. So you can get the value of effective mass at the different points here, and you can also get here at different k points. And, the ideal method is you have to get that effective mass at the lowest energy of this valence band and the maximum energy of this conduction band. So I think after watching this video, you will be able to calculate that effective mass for electrons and holes. So don't forget to give your feedback for this video, and thank you all. Now let me start.